This video goes over lesson 19.1. First, let's start with some vocab. A quadratic is a polynomial. Zoom in a little bit first before I start talking here. Okay, a quadratic is a polynomial with degree 2. Now, degree is the highest power. So, for instance, in this polynomial, we have 3 terms, and the highest power is 2. That's called a quadratic. The product property of square roots is actually listed right below, so we will fill that out when we get down there. But basically, it just says that when you have 2 square roots being multiplied together, you can multiply together their radicands. And the radicands are the numbers underneath the square root. Okay, so take a look at example 1. We are evaluating square roots, and these are all perfect squares, so they each have an integer square root. Square root of 36 is 6. Remember, that means that 6 times 6 equals 36. So what times itself gives us 121? That would be 11. And what times itself gives us 0? 0 times 0 equals 0. 9 times 9 equals 81. And 1 times 1 equals 1. So here we're talking about the square root product property of square roots, which is just exactly what we said in the vocab section. When we have the product of 2 square roots, we can multiply the radicands, and it goes the opposite way as well. When we have a product as a radicand, we can rewrite it as the product of 2 square roots. So for instance, the square root of 26 is the square root of 13 times the square root of 2. All right, so let's take a look at this method for simplifying radicands. So consider the square root of 24. Using the product property above, the square root of 24 is for the square root of 4 times the square root of 6. Now we break it down like that because the square root of 4 is 2. The square root of 6 cannot be reduced. So this simplification was made possible because we knew a perfect square 4 divided evenly into the radicand. If a person had written the square root of 24 equals the square root of 8 times the square root of 3, then no simplifying could be done because 8 and 3 are not perfect squares. Thus, the critical part is that one must choose factors that are perfect squares. And we'll get into that in this next example. Take a look at the list of perfect squares. These are the numbers that we are trying to see if they are factors of the radicand. So, example 2 is just all about simplifying radicals. Square root of 75. 75 itself is not a perfect square. So what perfect square goes into 75? So we start dividing. We want the biggest one possible, and we see that 25 is a factor of 75. So I write a perfect house and a not perfect house, and I call the radical a house, just to help you remember. And we are going to put the perfect numbers in one of them and the non-perfect in the other. And you only get to leave the house if you are perfect. So we're going to simplify square root of 25, which is 5, and square root of 3 gets stuck inside because they're not perfect. We're going to do the same thing for 108. Start dividing, and 108 is divisible by 36. It's actually 36 times 3. And so there would actually be a smaller perfect square that would go into 108. 9 goes into it, and so does 4. But we want the biggest one possible. And then we're going to simplify the perfect. So the square root of 36 is 6, and that 3 gets stuck inside. And we're just going to keep doing this. We always want to check our radicand and make sure it's not divisible by any other perfect square, and 3 is not. 63 is divisible by 9, so we do 9 times 7. And simplify the perfect. Square root of 9 is 3. 7 is not perfect. It gets stuck inside. And then 169, in my head I'm thinking that actually sounds like a perfect square. So I type in my calculator square root of 169, and I see that it is actually 13. So if you are dealing with a perfect square, just write the integer answer.